Okay, welcome everyone to our H seminar. It's my very big pleasure to introduce Alena Pirutka from New York University, from Courant Institute. And Alena will talk about local global principles and Bloch homology. Thank you.
Well, thank you very much for your invitation, and thank you all for joining. So today I would like to talk on some aspects of local global principles. From algebraic side, we will be interested in cohomological local global principles in the case of classical global fields and semi-global fields that emerged more recently and their extensions. And in the geometric case, we will be interested in zero cycles for varieties over finite fields, and we will see which cohomological invariants will appear in both cases. Well, I thought that maybe this subject could be more algebraic than expected at this seminar. So please stop me if you have any questions. And also, I put in the chat a link to a short version of this talk. I thought it could help maybe to follow. So it should appear in the chat and it will bring you to a PDF file. Some classical results first. The very famous Hasse-Minkowski theorem says that if you take a quadratic form with rational coefficients and you look at zeros, if you have a solution in QP for P and in the reals, then you have a solution in Q. It was proved by Minkowski for the field of rational numbers and then extended by Hasse to number fields. Next, we have central simple algebras and the theorem of Albert, Brauer, Hasse, and Nert. So we will take a cohomological point of view and need some notations. So when K is a field, we will be looking at the Galois cohomology group, where mu is a Galois module. In degree 2, and with mu n coefficients, you get the n portion in the Brauer, which classifies central simple algebras of order n up to equivalence. Now, in the case of global fields, if you take all completions at places of the number field, then the theorem says that if two central simple algebras become equivalent at all completions, then they were equivalent over the original number field. Now, these two results could be also viewed in a general framework of the question on triviality of torsors under linear algebraic group. So H1Kj classifies torsors, and then the question is this corresponding map when you look at completions for the number field injected. Then the previous results are positive answers to this question for two types of groups. For the orthogonal group, you get quadratic forms, and for PGLN, you get central simple algebras. So in general, the answer of this question is no. But according to Kneser's conjecture, which is now proved, it is true if J is a semi-sample simply connected algebraic. Then, of course, extensions of these results and these questions for different types of groups, for other fields, is a large subject. But for today, I will be interested in something different. So for this talk, we will be looking at higher degrees, finite coefficients, and the semi-global fields. This will be for the first part. And as I said, for the second one, we will be talking about zero cycles. So I need to fix a setup for the first part. So here we're looking at a field and a collections of overfields. So these KVs are not necessarily completions, and we will specify in each case what do they mean. Again, we're looking at a Galois module and a Galois cohomology in degree n for the field and for the overfields. And we want to know when the corresponding SHA group is a kernel of this map is trivial. As we've just seen, if we take a number field and the omega corresponding to its places, then SHA2 is 0. Okay, now I would like to list the fields of our interest for the first part. So global field as before. Now the semi-global field. We first look at a local field, complete discretely valued field with finite residue field. So this assumption that the residue field is finite is not necessary for all results that I'm going to talk about, but for simplicity, I decided to fix this assumption for the talk. And E, the semi-global field, is a function field of a curve over a local field. So it is known that this curve has a regular proper model over the ring of integers. So here there is a little illustration. You have the ring of integers and the relative curve with the generic fiber and the special fiber. Here the set of overfields is again corresponding to completions at all discrete valuations. So here, as example of discrete valuation, you can take, say, a component of a special fiber and a generic point, and look at the order of vanishing of functions at this generic point of a component of a special fiber. So this will give you an example of a discrete valuation. Now, local global principles over semi-global fields were studied by Harbater, Hartmann, and Krashen in the context of patching, and then also by Quillen, Parimal, and Suresh, and others. We will list the local global principles in the next slide. First, two other fields. Here, this is the situation studied by Kata when he looks at the field of transcendence degree 1 over global field. So here, Y is a geometrically integral curve, and the set of overfields corresponds to partial completions. So you see, you take a completion over global field, then the curve over this extension, and the function field of this curve. Now, motivated by this, his work, we were looking at a field of transcendence degree 1 over semi-global field. So here, C again is a curve over a semi-global field, and the overfields again correspond to partial completions. You take the curve over the completion of a semi-global field, and then the function field of this extension. Okay, so now I would like to list the results on SHA groups for these types of fields. K global, L is a Kata situation, E semi-global, and F is the field we studied. Okay, so we already know one case here. This is again Albert Brauer-Manin receiver. Then we will be looking at an extension of transcendence degree 1 of this field. And here, Kata shows that the local global principle holds in 1 degree higher. Okay, now we are arrived at the semi-global situation, where Harbater, Hartmann, and Krashen proved the local global principles in degree 2 and 3. Okay, then again, we're looking at field of transcendence degree 1 over this field. And similar to what Kata did, we found local global principles in 1 degree higher. Okay, so now I would like to fill in the remaining parts of this table. So first, this group where we're looking again at the curve over a global field. Here you can show that SHA2 can be non-trivial. In fact, if we assume that the curve has a point, and if we look at the Hochschild-Serre spectral sequence and do a small argument, you can see that this SHA2 group for this special case of overfields is actually isomorphic to the classical Tate-Shafarevich group of the Jacobian of the curve. And we know that this is not necessarily zero. For instance, for a Selmer curve, a cubic curve, this will not be zero. Okay, now this corner, we also have all non-zero groups. Here for SHA-1, it's a result of Collet-Alena and Parimal and Suresh. And then using this result, we prove that in those two cases, you get non-zeros. And I guess in these two cases, you get zeros, and this remaining parts, probably besides the real component, are ruled by the cohomological dimension. So this is the picture, and then I would like to talk about the proofs for the column we were interested in. As you will see, they proceed mostly by reduction to the other known results. But however, I think that this table just confirms a principle that if you have a global field, a local level principle over a field, and then you extend its complexity by one, you're looking at a function field of the curve, a field of transcendence degree one of the field, then you expect that the local global principles will hold in 1 degree higher, which is confirmed in these two cases from K to L and from E to F. Okay, so before discussing proofs, just one comment that, of course, this set of overfields, as we said, they correspond to partial completions, and this could seem rather special. So we may wonder whether we can instead look at all discrete valuations on F, which is probably a more common thing to look at. But it so happens that these partial completions behave a little better. However, in degree at least 3, you get the same groups, but this is not formal. So this quality actually uses that the results on SHA groups for the semi-global field. Also, here in the notations I took for the module mu L tensor n minus 1. Again, you can look also not necessarily at prime L and not necessarily n twist n minus 1. But for the talk, I decided to keep this for simplicity. Okay, so now I want to discuss proofs in this column. First, for non-vanishing, SHA-1 and SHA-2, and we just come up with some examples. So the example is actually really easy. You take as a curve projective line, and in this case, you can derive a sequence which is an analog of the Fadeev sequence for the Galois homology of the function field of P1. So here in the middle, we have the group we're interested in. Then on the left and on the right, we have the SHA groups for the base field, which is a semi-global field. Here, we're interested in degrees 1 and 2. So in this way, we can reduce the study of our group to SHA-1 of the semi-global field. So for n equal 1. And for n equals 2, we look on the right-hand side. And again, we find SHA-1 of this field, which is an extension, but it's still a finite extension of E, but it's still a semi-global field. Okay, so in this way, we'll bring back this sequence, but I just want to recall the table that SHA-1 here is not necessarily 0. So this is basically the end of the proof. We can use it, it's non-zero. And precisely it's non-zero when for this semi-global field, if you look at a regular model, when the reduction graph of the special fiber is not a tree, then you can get that SHA-1 is non-zero. So this gives you the non-vanishing here. Okay, now for, I actually want to say that this also holds for, in the case of complete discretely valued field, not necessarily local. So this is the same proof goes. Now for the vanishing for SHA-3 and SHA-4. So here we're in the situation where F is a field over E and over K, and we will take a regular proper model of F over the ring of integers of K. So this will be a relative surface such that the special fiber of C is a simple normal crossings device. Okay, so this does not necessarily exist just when we keep F. However, it exists by the Young-Gaber alterations theorem, exists up to an alteration of degree prime to L, which is enough for our purposes. And as I said, now we will use reduce the vanishing results to other known vanishing of invariants. Okay, so here we're looking at the field F and this group, which is a group of unramified cohomology of F over C. Defined in the following way, you look at all points of codimension 1 of the model C. Such point, as we recall before, defines a discrete valuation. And to such discrete valuation, you can associate the residue map, which goes to the cohomology of degree I-1 of the residue field of the point. And in these two cases, this unramified cohomology is 0. So these are very difficult results. So one is for by Saito and Sato, and which is special for degree 3. And in degree 4, it is a result of Kers and Saito, which also holds for varieties in higher dimension for corresponding values of I. I increases with dimension. Okay, so here with some work, you can show that these subgroups we are looking at are subgroups of this unramified cohomology groups when n is at least 3. And once you know this, you can use this results to show that in these cases we get zeros. Okay, so I want to comment a little more on this invariance. So this is probably a good time to introduce it in general. Yeah, so here we will be looking at these groups later, so that's why I want to put it here. In general, if we have an integral variety over field, similar as before, we're looking at the function field of this variety. And if you look at discrete valuation on this function field, then to each valuation, you associate a residue map. And the unramified cohomology is the intersection of kernels of all these residue maps for all discrete valuations of rank 1. This is with finite coefficients, and with infinite coefficients, you just take a limit. Okay, so now coming back to the case of the field F, again, we took here the set corresponding to partial completions, and there are other set of overfields which is possible. For example, you might wonder, what if we do not include the valuation centered on the closed fiber and look on the generic fiber of the initial semi-global field? Well, then you can see that actually you do not get any vanishing of SHA in degrees 2, 3, and 4. Okay, so this is all for the first part, where we looked at the function field finally of an arithmetical threefold, because this is what F is. And next, we will switch to a geometrical situation and to a threefold over a finite field. And we will be interested in this group, the H3 unramified, in the case of trivial fibration over a curve, a surface product with a curve. So this case could look quite special. So I want to first discuss some background and motivation why we can be interested in studying this. Okay, so I need some setup for the second part of the talk. So here again, we start with a global field, which could be a numbered field or global field of positive characteristics. And again, we will be looking at all completions. So at the very beginning, we started by recalling the Hasse-Minkowski theorem, where we were interested whether a quadratic form has a 0 over k. Well, of course, more generally, if we have a smooth and projective variety of a global field, we want to know whether it has a point. More generally, we may wonder if there is a zero cycle of degree 1. So this means we'll be looking at the closed points where the degree is 1. Okay, here, if we look defined by the index of x as the greatest common divisors of degrees, so having a zero cycle of degree 1 would correspond to the case that the index is 1. And we want to read it from a local data. So what if the index of varieties over the completion, so this is xv is x over completion, what if these indices are ones, and do we have also that variety x has a zero cycle of degree 1? So I don't think that SHA-I is a standard notation, I just put it for the talk. Okay, I want to first give a positive result in this direction. So here we over a number field, and x is a geometrically rational surface. So by a theorem of Quillen and Kahn, we do have this local global principle for zero cycles of degree 1 under the 3 hypotheses. K is totally imaginary. The second hypothesis is essentially that there is no Brauer group. And the third invariant, well, could be viewed as something in a similar framework as the first part of this talk. So this is where you look at H3 unramified of X, and you look at elements that vanish for all XVs. Okay, so I want to comment more like on this third part, besides the fact that one conjectures that it's always 0 for a geometrical rational surface. But I want to talk about the second part. So it is an assumption that the Brauer group is trivial. So what if it's not trivial? Then it is well known that you can have a so-called Brauer-Manin obstruction. Okay, so let me recall what it is. So here we're looking at a variety of a global field of any dimension, smooth and projective. The Brauer group is the cohomological Brauer group of X. And then for each place V, you have the local invariant, which is a pairing of the group of Chow group of zero cycles with the Brauer group. This goes in the Brauer group of the completion. And this local invariants satisfy the reciprocity principle, which is if you take a cycle, zero cycle that comes from X, then for any element of the Brauer group, the sum of local invariants for this cycle, which we can view also over XV, is 0. Okay, so this cycle, if it comes from X, it induces a family of local zero cycles, which is orthogonal to the Brauer. Now, you can ask for a converse statement, works of Quillen and Saint-Sucre on geometrically rational varieties, and then of Kato and Saito led to the following conjecture that in this situation, the Brauer-Manin obstruction for zero cycles is the only one. In other words, if you take a smooth projective variety, so it's not necessarily a surface, it's just any smooth projective variety of the global field, and if you assume that there is a family of local zero cycles of degree 1, so each one is of degree 1, this family is orthogonal to a Brauer group, then the conclusion is that X has a zero cycle of degree 1. So although there has been a lot of progress on this conjecture over number fields, it is open in general. And next, I would like to switch to the case when the global field is necessarily of positive characteristic and discuss the connection of this conjecture with other cohomological invariants. Okay, so here a global field of positive characteristics, function field of a curve over a finite field. We are interested in a variety X over this global field. And we assume that this variety has a global model over the curve. So here V is smooth and projective, not the map, but just the model V, we assume it is smooth and projective. Now, there is a theorem by Saito, where he looks at the cycle class map for 1 cycles on the model V with the L coefficients. So if this map is surjective, and if there is a family of local zero cycles of degree 1, which is orthogonal to the Brauer group, then, well, it's not that X has a zero cycle of degree 1, but it has a zero cycle of degree prime to L in this case. So this is a prime to P version of the conjecture we've just discussed. Okay, so anyway, this is then related to the integral Tate conjecture, which is the surjectivity of the cycle class map with ZL coefficients for 1 cycles. So there are not many cases of the integral Tate conjecture that are known. There are some counterexamples, and there are a couple of cases where it is known. However, in the case for 1 cycles, as far as I know, there is no known counterexample for the integral Tate conjecture. So for now, no counterexamples for the assumption of this theorem. Okay, now one can also relate this prime to P version of the conjecture on Brauer-Manin obstruction to the H3 unramified cohomology. So this is our next slide. It's a theorem of Quillen and Bloch. Here, again, V is a smooth projective variety over a finite field. And we're looking at the cycle class map with ZL coefficients, but this time for cycles of codimension 2. So before it was for 1 cycles. And here we'll have cycles of codimension 2. Then the torsion of the cokernel in the cokernel of this map is H3 unramified mod its maximal divisible sum. So conjecturally, by Tate conjecture, the cokernel is torsion. So conjecturally you remove this part. And also the H3 unramified is conjecturally finite. So you can also remove the maximal divisible sum. Now, for varieties of dimension 3, we can put this theorem and the theorem of Saito together and get the following statement. Here we're looking at a 3-fold. So this is the model of the model V over the curve. V is smooth and projective, it is a 3-fold. And X is a generic fiber, the variety of a global field we're interested in. Assume that the Tate conjecture holds for divisors on V, and that H3 unramified of V is 0. Then, if there is a family of 0 cycles of degree 1, which is orthogonal to the Brauer group, then X has a 0 cycle of degree prime to L. Okay, so this brings us to the study of the H3 unramified for 3-folds over finite field. And the question is whether the second condition is always true. If it is, then under the Tate conjecture for devices, you have the prime to P Brauer, that the Brauer-Manin obstruction is the only one for the 0 cycles of degree prime to P. Okay, so now is H3 unramified 0? So I want to list the known cases for this question. Okay, this is our question. The answer is yes, when B is fibered in conics over a surface. So this is a result by Parimala and Suresh. So this second part, I'm going to give you more details next. So it is a case of a product of a surface and a curve under some assumptions. So I looked at the case when S is very close to be geometrically rational. And then in works of Quillen and Scavia, and then by Scavia this fall, they looked at the case where, in particular, you allow Enriques surfaces. So as I said, we'll talk about this in details later. Now, this third part is a conjecture that the H3 unramified should be 0 if V is geometrically unirooted. So this is motivated by result of Quillen and Voisin for varieties of dimension 3 over complex numbers. So if V is uniruled, then H3 unramified is 0. And this uses results on integral Hodge conjecture by Voisin for uniruled triplets. So for now, in the case of finite fields, it is a conjecture. There is this following open question. I think it is still open and has been open for at least a decade, if not two, which is surprising because it's very concrete. So here you take a product of 3 elliptic curves over a finite field, and we assume that there are some elements of 2 torsion. And then you look at the cup product. So this cup product will induce an element in the cohomology of V, and as such, it gives you an element in H3 unramified when you look at the image over the function field. But now the problem is to know whether this cup product over the function field could be non-zero. Well, and this is not known. But over the complex numbers, it could be non-zero if you change F by C. So there are this case is understood. However, F is finite, and the closure, the real closure is countable, so that so there is a problem to adapt the result of complex numbers to this case. Now in other dimensions, so we're talking about dimension 3, but let's see what is known in other dimension. 4 is also open. In dimension 5, it can be non-zero. In dimension 1, it is by cohomological dimension, it is 0, and by theorem of Quillen, Sansuke, and Soule, it is also trivial in dimension 2. Okay, so now I want to discuss this second case more in details. So here C is a curve and S is a surface. We will always assume that S is geometrically CH0 trivial, which means that if you look at 0 cycles with rational coefficients, then degree map gives you an isomorphism with Q for any algebraically closed field that contains the finite. As examples of the surfaces, you have geometrically rational surfaces, or in positive characteristic, you have supersingular case 3 in Schrödinger sense, and the Enriques surfaces as well. Okay, now the more precise list of results for the triviality of H3 unramified for these types of varieties. So I looked at the case when their H1S or S is 0 and neuron severity, geometric neuron severity of the surface has no torsion. Then Quillen and Scavia looked at the case when they do allow the torsion, but you need this vanishing result where G is the Jacobian of the curve C. And they also needed the Tate conjecture for divisors on surfaces. And lastly, Scavia this fall removed this condition on the Tate conjecture, but he needs one more vanishing property, for F group schemes, the peak zero of the surface and the Jacobian of the curve. So now I would like to discuss the proof of the first case, which naturally I know better, and also give you maybe an overview of the proof of Scavia, and especially just the idea of where these two assumptions are coming from and where they are needed. Well, before doing this, one example of a product of an Enriques surface and the elliptic curve. So this is the last Scavia's result, and it does apply to the case of an Enriques surface and an elliptic curve, such that the curve has no true torsion over the finite field. Well, as well known, you just need to take the curve as this equation where f is irreducible of degree 3. So his approach actually starts with the integral Tate conjecture, and then he derives the vanishing of H3 from the fact that the Tate conjecture holds in this case. So he proves that for one this integral cycle plus map for cycles of dimension 2 is surjective for this product over a finite field. Well, however, one of the reasons I wanted to talk about this is that this is in contrast with the situation over the complex numbers. So by a recent result by Benoit and Autumn, the same settings, but for Enriques surface over complex numbers and E a very general elliptic curve over C, then you have that the integral Hodge conjecture does not hold in this case. Okay, so now a few details on the proofs. First, a general strategy and couple of facts. So coming back to the definition of the unramified cohomology, probably you remember, or you can look at the slides that I shared in the chat, that it was defined when you take the valuations that correspond to all, when you take the all discrete valuations. Now, when X is smooth and projective, it is actually enough to take valuations corresponding to points of codimension 1 on this smooth and projective model. So in this way, if you look at the étale cohomology of the model, then all these residue maps will vanish on these classes, and this gives you a map that I denoted here tau, from the étale cohomology of variety to the unramified cohomology of X, which is a subgroup of the function field. So you just restrict the classes to the function field. However, as we've seen with this example of elliptic curves, the kernel is mysterious, and this starts in degree 3. In degree 2, it so happens that for H2 unramified with mu L coefficients, you get the Brauer group. And then you have an injection for a smooth projective variety of the Brauer group to the Brauer group of the function field. But starting from degree 3, it is unclear. What can you say on the kernel of this map? Well, however, it so happens that in the special case of the product of a surface and a curve, this approach of looking at the cohomology of the variety actually works. So here, how the strategy goes. So you first look at this surface of this function field. Then this threefold is a trivial fibration of a surface over the curve C. And then you look at the generic fiber, which is just the surface extended to the global field, the function field of the curve. And then first you lift the unramified classes here. Then a little more work, you lift it to the H3 of the threefold. And then you show that in this case, well, actually this map tau is 0. Okay, so a couple more details on this. For this, I will need to recall the formalism of Bloch-August, which is known probably from the 80s and 90s of the last century, but I think it's still useful to recall how it works. So at the end, we're interested in this blue exact sequence, which, as you see, has this map we're interested in, the cohomology in degree 3 of the variety to the unramified cohomology. So it appears in the sequence. So let's see how we obtain this. So in general, it applies for any smooth projective geometrically integral variety. And here we're looking at a complex, which starts as the unramified cohomology definition. So you look at the function field of the variety, and then you have residue maps for all points of codimension 1. So you arrive at hi minus 1. Then here, each residue field is a function field of a variety of dimension 1 less. And then you look again at points of codimension 1 of this variety and again at residue maps. So you arrive at codimension 2, and then you continue until you arrive at codimension I and the group H0. So the Gersten conjecture in this cohomological setting says that this complex is a resolution of a sheaf associated to H, which from U and open, the risky open, you compute the étale cohomology of U. Okay, now looking at this complex, you see that because X is a smooth and projective, then the zero cohomology, just the kernel of this map, is HI unramified. But also, if you go to the very end, if mu of minus I is Z mod n, here you just get a sum of Z mod n for points of codimension I, and the previous map is actually given by divisors of functions. So in this way, in the last co-kernel, so HI of this complex is Chow groups of codimension I of X mod n. Now, in this setting, you have a local to global spectral sequence, which converges to the étale cohomology of X. Okay, so these few points probably explain how do you get in one sequence the Chow group of cycles, the étale cohomology, the unramified cohomology, and H3 étale of X. Okay, so we get this from this spectral sequence, and now we are interested to show that the first map is surjective. In our particular case of threefold over finite field. Okay, so let's see. Oh, we actually need, before doing this, we need one more slide on the Gersten conjecture for in the case of K theory sheaves. So here we're interested in two blue lines in the middle, and I just want to briefly comment on where they're coming from. So here NH3 is the group we're interested in. These are again the classes in H3 étale, which goes to 0 to the function in the function field. And this group sits between cycles of dimension 2 and this cohomology of K2 sheaf. So this K sheaf is again associated, is obtained by associating to U the Quillen's Ki of the ring of global functions on U. And it has a resolution which is similar to the one we've just discussed. You look at the residue map in the case of Ki for points of codimension 1, and then continue for points on codimension I. Now, by Mercurius consistence theorem, which is degree 2 case of Bloch conjecture, if you take K2 of a field mod n, this is isomorphic to Gallo cohomology of K. So putting this all together, you obtain this sequence. Well, I'm not explaining how, but maybe it's clear that how to proceed. And also the first map is obtained just by the explicit description of the cohomology of K2 from this complex. So it receives a map from peak X times the constants. So these are elements of the base. So we will need this a bit later. Okay, so now first, the first sequence we discussed applied to our set. C is S is a surface, and I want to apply the sequence for X the surface over the function field of the curve. Okay, so I have the two cycles of dimension 2 on the surface of a K, then this group, and the H3 et al. Of the surface over the globe. So we want to show that the first map is surjective, and for this, it is enough to show that the group of 0 cycles of degree 0 here is trivial. Okay, so at this point, we will use that there is no torsion in neuron severity. So then the peak S bar is the torsion-free of finite type Galois module, and then you can look then at the torus, which is dual to this. Now, in this situation, Collier, Talent, and Sansu can independently Bloch looked at these maps that allow to study the group of 0 cycles via the cohomology of the torus. And we look at then these maps for K and for the completions. So we first get this big square in this way. And for the lower row, this is H1 of the torus, H1 of the completion, and the kernel is the SHA group. Now, because of the assumptions on S and the construction, it is quite easy to see that the diagonal map is 0. Basically, because it would factorize through H1, not over the completion, but actually over the residue field, which is a finite field, and that's how you get 0. Now, the properties of this map do imply that so for this assumptions, with these assumptions on the surface, the kernel of this map is 0. So phi this is injective. So injective and diagonal is 0. So that is enough to show that the SHA1 here is 0. So if SHA1 is 0, then you'll get the A0 is trivial because of this analysis. Okay, so this brings us to this study of the SHA1 of the torus. And this is where we are going to use that. We've actually started with something that was defined over F. And the torus has a so-called flask resolution. So here is a torus. A P here is a quasi-trivial torus. And F is flask, but by Andamiata theorem or over finite field, any flask torus is a direct factor of quasi-trivial. Okay, so with this sequence, then we see that the SHA1 we're interested is included in SHA2 of this flask torus. And because it's a direct factor of quasi-trivial, it's enough to show that SHA2 of this torus is trivial for a finite extension. Now we have Shapiro lemma that says that actually it's enough to show that SHA2 of GM is 0. But this way we're again using the Albert Brauer-Hasse-Noether theorem that we talked about in the very beginning. So this is exactly what we need in this case. Okay, with this argument, this gives a lifting from the group we're interested in to the cohomology of the surface. Okay, now a few comments on how to continue. I think this, I'll have less detail on that. So this is what we've done. We looked at the H3 and ramified over surface over the global field, and we showed that the first map is surjective. However, here we did not look at the valuations that were non-trivial on K, and this group we're interested in is smaller. So now we want to account for the missing valuations on K. Okay, so how do we do that? So because of the assumptions on S, you can look at the Hochschild-Serre spectral sequence and you see that this cohomology in degree 3 is in this way isomorphic to H1 of the global field of with this module. Now we have some missing valuations on this field, right, from here. And I want to apply them on the right-hand side because it's much easier to deal with H1 here than with this H3 on the left. So for this, you need some compatibility property of this border map in the spectral sequence and the residue maps. And it so happens that it is true. And so if you start with something in this subgroup, which satisfies that all the residue maps corresponding to the evaluations on K also trivial, then because of compatibility, you have that the image here actually comes from the curve. And because it comes from the curve, you're looking, you can see that this cohomology of the curve is also receives a surjective map from H3 of the threefold. And that's how you obtain the lifting of a class to the H3 of the threefold, just by looking at its image here, applying the missing residue maps, deducing that then it comes from here, and so that you can lift it to H3. So it's a little heavy to write, so I just decided to illustrate it with this diagram. But anyway, with this argument, you managed to lift everything to H3, and now what remains is to show that the image of H3 in the function field is 0. So just briefly what it uses. So first, so we interested in a group with infinite coefficient, but actually by Mercouri-Psusten theorem, the L torsion of this group is the group H3 with mu L coefficients. So in this way, it is enough to consider these finite coefficients, and by restriction, co-restriction, you can even assume that mu L is lives already in your finite field. Okay, so why do we need that? Because in this case, we can replace mu L by Z mod L coefficients and use Kummer for the extension to the algebraic closure. So in this way, you get that this cohomology of the threefold is given by this product of peak and H1 of the curve. And now we use, so this is just a sketch. So we use the two properties from the general Bloch-August formalism. So here is, so we're interested in the peak and H1 of the curve. The H1 of the curve, we view it in the function field, and then we send it to the H1 of the K2 sheet. Now it so happens that here we of course over F bar, but because of the assumption on the surface, the Galois action here gives you exactly the group H1 of the surface over the global field. So you can remove the algebraic closure and you're back to the finite field. And this, as we have seen, it is a subgroup of the group NH3, exactly the group that we want, of classes that are trivial if you go to the function field. So it is very much a sketch, and there are more arguments that I needed to make it work. But I just wanted to illustrate what we're using and just comment that here we have the Kummer isomorphism and the Galois action, which is important to understand in our case. So this is all on the proof for the H3 unramified of the product of the surface and the curve when the surface has no torsion and neuron severity. Now, this is the last slide with an overview of the Scavia's approach in the case when you do allow some torsion, but you need this vanishing properties. So he deduces the result in H3 unramified from the integral Tate conjecture. So it's enough to show that the integral cycle plus map is surjective, but this is not formal. It uses an argument with correspondences, but also the assumptions on the surface. Now, with more work, he shows that it's actually enough to look at the Ital cohomology of the bar fixed by the Galois action. Again, this is a subtle analysis of the Hochschild-Serre spectral sequence for this H4 group and the Quillen decomposition, and with the L coefficients and the properties of the surface. Okay, and now once you have this H4 over the algebraic closure of this Galois action, this assumption, as far as I understood it, is used to derive that the invariance under the Galois action here is exactly the H4 of the surface and the H2 of the surface. So you cannot have anything else coming from the curve, and that's where you use this assumption. So now once you have this is basically done just from this diagram. So this is the map we're interested in for this threefold. Now the cohomology group is isomorphic to this direct sum, which receive maps from the zero cycles on the surface and the curves on the surface. So the red map, so this is zero cycles on the surface is geometrically integral over a finite field. So the red map is surjective by the Langevin estimates. And then the blue map is surjective because of the assumption on the surface. So because it's geometrically trivial, it also satisfies that B2 equals rho. Well, this is the end of this strategy. Okay, so this is all I wanted to say for today on these different invariants and open questions and some of the results we were able to do. Thank you so much for your attention.
Thank you, Alena. Thank you very much. Thanks, Alena, for excellent talk. And Zoom like this. I did already. Okay, so let me stop recording.